Hello, Gita, can you hear me?
Hello, Professor. Yes.
Good, okay. Here's your Excel exercise spreadsheet. Why don't you take us through your thinking behind the forecast?
Yes, sure. So what I did is downloaded the exchange rates for the past from 20th of March.
Uh-huh.
I've copied one column down on the D side, so that USD exchange rate was Y at T, and the next column was Y at T minus 1.
So here is the current exchange rate. And this is the lag, is that correct?
Yes.
Okay. So let's take a look now at your econometric exercise. And what have you found out?
Yeah, so I've plotted, I did, what's it called? Give me a second.
So you have regressed the exchange.
Yeah, I used regression model for both of those columns, and I had those outputs, and checked that the standard residual was not above 2. It does not exceed.
Okay, good.
Yeah, no outliers.
One is very close right here.
Well, it's close, but it's not. I tried another. I tried taking more samples, and I had quite a lot of values on a standard residual that was well above 2. So it was like 3 something.
Good.
So yeah, my forecast for the 2nd of April was 122.88 tenge.
And how did you arrive at that?
So I've YT equals to a coefficient of intercept plus the coefficient of x variable 1 times by the lag.
Okay, good. So in the forecast, you had inserted for the lag the value of the exchange rate today into the bottle, and that's it.
Yes.
But wait, what is the exchange rate today? Let's take a look. So
26.
What is it? Say again.
I guess it is 426.
426. Okay. So back to your forecast. You are really rather close, considering that we only had 13 observations in this model. The one strip that has forecast operates very well. You have 423. The actual exchange rate was 426. Good.
Yeah.
So, by the way, here's one way of interpreting the residuals. So here is the current exchange rate, the actual rate, and then y hat is our forecast of the exchange rate based on the model over here that your son is using. So this is y hat. The difference between the two is residual. So the residual is measuring the mistake in the forecast. Then we are using past values and trying to forecast or predict them. So for example, for our first year, we have the standard residual and the residual that are positive. So this means that our model of the exchange rate has under-predicted. It is below the actual exchange rate. And then for year two, we have a negative residual. So what does that mean in terms of the understatement or the overstatement? This time, the actual exchange rate is above the prediction. So now our model is under-predicted. And it's very interesting to see that in most of our residuals, that the sign is negative rather than positive. So there is a tendency in this model to under-predict. So that's interesting. Maybe we need to add another independent variable that would explain why the model is under-predicting. One possibility is that maybe we should take into account the inflation rate. That is, the increase in prices on average. Now let's see if I can do a better job of spelling this time. Usually when prices are rising in the domestic economy, eventually they will cause the exchange rate to rise as well, since inflation means a loss or depreciation of the value of the exchange rate, the value of the penny in terms of dollars. If the exchange rate is rising, the foreign value of the penny is going down with inflation. Okay, so why don't you now tell us, Yuzhan, what you have in mind for the confidence interval, the level of interval?
Is it the same thing, confidence level and interval?
I don't know. I've always used the term confidence interval because we're talking about a continuum of values.
So yeah, I've placed my forecasted value for the 2nd of April in a column, in an added forecast value, and I've constructed the wait a second. I've constructed the descriptive statistics model.
How good this in itself, that's just very good.
Yeah, and it came as this, and my lower bound was the confidence level, the mean minus confidence level, and the higher bound was mean plus confidence level, and so the confidence level is the range between the higher and the lower value.
But you see, you're on the right track. But what you really have is not the coefficient interval, but instead the independent variable, column 1. So the mean exchange rate is 423 and so forth. The confidence level here doesn't really mean a big deal to us because we're not interested right now in the fluctuation of the exchange rate. Instead, we want to have a measure of fluctuation in the coefficient, not the independent variable.
Okay.
So you have a model that looks like this. You have an intercept and then a coefficient on the independent variable. This is a dependent lag. Your confidence level over here refers to like T minus 1, but that's not what we want to know. We want to know how much fluctuation, how much giving, how much oscillation there is in the coefficient. The coefficient is a random variable that differs from one sample to another. Okay, so here's a problem. We have a pre-estimate. For the forecast of 422. But in a way, the pre-estimate does not give us very much information about the model. In this case, the actual exchange rate for today was 426. Now, how do we interpret that? Does this mean that our model is good because they have missed the actual value by only 4 pennies? Or is this a bad model because 4 pennies sounds like a lot of difference to us? Is this model accurate? Fairly accurate? So far, we can make either case. We could say that yes, this model is accurate. Because the model underpredicts. but only for Katie. Or somebody might say, no, this model is not accurate because it underpredicts by 4K. And that's a lot. So we have a problem in deciding whether this is a good or bad model because we don't have a consensus on how close the forecast should be to the reality before we can approve the model. So right now, we don't know whether we should use this model again. So the solution is to use for the forecast not just the point estimate, but also the confidence interval. So for the 95% confidence interval, we are, roughly speaking, 95% sure that the actual exchange rate will occur in the interval if we have a good model. So what we will do to gauge the accuracy of our model is to check on whether or not the forecasted exchange rate occurs within that interval. Uh, for that exercise, we will need primarily the average error in the model overall. In other words, most of the fluctuation limited the error. And our forecast is due to the overall model. So, for example, in this case, they have found that most of the mistakes are underestimates using our observations. So, since we can form an underestimate, of past values, it's not surprising to find that a forecast of 423 is an underestimate as well. So we can measure the error in the overall model by using the standard error of the estimate. So very roughly, this measures the average mistake in predicting past values of the exchange rate. If our average mistake is large, we can anticipate that maybe there will be a large mistake in our forecast as well. And there is the standard error of the estimate with about 0.78. By the way, these tables of above regression are sometimes called ANOVA tables. ANOVA for analysis of variance. Okay, so now how do we get an estimate of the fluctuation that may occur in the forecast if they are moving from one sample to another? Well, now our standard error of the estimate can help us out. We assume that the exchange rate is following a normal distribution. In fact, a standard normal distribution of if we are standardizing the exchange rate. So this means we're going to put it this way. In general, a normal random variable will fall between the lower bound, which is the mean value, minus 2 times the standard error. This is the lower bound, and then the upper bound is our estimate plus 2 times the standard error of the estimate. Not 1, but 2. For 95% confidence, So before we estimate this confidence interval, let me just for a moment go back to a graph that may or may not help, depending on my skill as a graphic designer. Okay, so on the horizontal axis, we have a random variable, or we'll just call it x, a normal random variable. So, for example, our forecast of the exchange rate may vary from one sample to another. Our forecast is a random variable. And then over here on the vertical axis, we will measure the probability of showing a particular value of x in terms of relative frequency. So this is what we have. We have a normal distribution that means that we have a bell-shaped curve. And now we will have to pardon my poor draftsmanship. Do something like that. Although it should have the bell shape, there's a symmetry on either side of the mean value. Okay, so as an example, we have a value for an interval of x values that looks like this. The area right here, the area here is the probability that our value of x will fall between x1 and x2. Now, let's take an extreme situation. Since our probability is cumulative, we will add the probability as we are moving from the left over to the right. So, for example, here is x3. Corresponds to of this vertical line, another value, a low value this time for a random variable. All right. Now, in this case, the probability that we will draw a value of the random variable that is no higher than x3 is 5%. Five percent is measuring the area beneath the bell-shaped curve to the left of x3. This is the area. So in this case, there is a 95% chance that x as a random variable is larger than x3. And then we can do the same thing on the right-hand side. So here's x4. And there is, given our assumptions, a chance of only 5% that x will be higher than x4. So there is a 95% chance that f is smaller than x4. To put it another way, there is only a 5% chance that x is smaller than x3 and only a 5% chance that f is larger than x4. So in other words, if we have a normal distribution and a good prediction of the mean value of x, then there is a 90% chance that x will fall within this interval from x3 to x4. So there is a 90% chance that x will fall in the interval of x3 and x4 like that. This is the 90% confidence interval to x. Okay, so far. So this same reasoning will apply to the 95% confidence interval. You just have a wider range of possibilities. So, for example, here is x5. That much of 2.5% of the possible values of the random variable x. That is, this area right here accounts for 2.5% of the cumulative probability. There is a chance of 2.5% that x will exceed x5. And the same thing on the extreme left. Right there. In other words, there is only a 2.5% chance that x will be lower than x6. So this time, a confidence interval is x6 and x5. So what is the percentage of our confidence interval this time? We have already seen the 90% composite interval is. Now, what is it for x6 and x5? But let's see, we say that there is only a 2.5% chance that x will be smaller than x6, and only a 2.5% chance that x is larger than x5. So there is a 95% chance that x will fall between x6 and x5. So that is a 95% composite interval. Okay, so far. Okay, so here's an example using a good model. Here's for test that the exchange rate will be 423. So this is like an average exchange rate across all samples. Here's the mean exchange rate will be 423 across all samples. Here's the mean estimate. Again, I apologize for my clumsiness as a graphic artist. That estimate is based on a sample of past observations. Now, they have seen that the actual exchange rate in the real world, not just in the sample, the actual exchange rate is 426. So the question is whether they have a good model that they can use again to foretest the exchange rate. And the answer is yes, we have a good model if 426 falls within the 95% interval, like that. But assuming a mean value across all samples of 423, it's a hypothesis. So there is one possibility, but here is another. maybe 4/25 falls over here. That is outside the company's interval. We have a bad model if 4/26 falls outside of the 95% confidence interval. Because chances are low, are very low, no higher than 5%. That we will observe and exchange rate according to ER that is outside of the confidence interval if our expectation of 4/23 is correct for the overall statistical population. So I'm going to clean up this a bit. So that's the reason for calculating a 95% confidence interval for our forecast. It is almost impossible that the actual exchange rate will equal exactly 4/23. But that's not what we want to know. We want to know whether or not the actual model is close enough to our prediction to justify using the model in future forecasts. Okay, so now just one more thing to note. Given a normal distribution, the confidence interval is equal to the range, in this case 4/23 minus 2 times the standard error of the forecast. So there is the lower bound, and then what would you guess that the upper bound would be? the mean plus 2 times the standard error. The reason for that is that given the normal distribution, by SE by mean standard error. In general, the distance from the mean, I'll call this S1, and of this high value, I'll call it X2. This range here is equal to the mean F1 plus 2 times the standard error. Let's see if I can draw this right here. That range on the horizontal axis amounts to F1 plus 2 times the standard error. And the same thing on the left-hand side from the mean of X1. This range here between X1 and X6, the distribution, amounts again to 2 times the standard error. So there is the justification for using 2 times the standard error to measure the fluctuation from the mean of X. So in this case, the composite interval 95% composite interval varies from F6 to F2. And we think that our model, that in this case, CDX 4.3 is the exchange rate, that model is good enough to give us an interval of possible values that are very likely to occur. Okay, so far. Okay, so let's now go back to Urzon's model. So more or less, the standard error of the forecast is largely equal to the standard error of the estimate in the regression. So our lower bound in this case is 423 minus 2 times the standard error, which is 7.8. Or 421. And then the upper bound, same idea. Add to our expectation 2 times 0.78 for an upper bound of 425. So the 95% probability interval in this case ranges from about 421 up to 425. So the actual exchange rate was 426. Do we have a good model or a bad model in this case?
Bad model.
Maybe. I mean, it's just very close. The upper bound was 425. We were almost there. So this model that I gave to you, and also regressive model that is based only on the past value of the exchange rate can be improved. That's the idea. Maybe by adding the rate of inflation as an independent variable. Okay, so I have 8 o'clock right now. Would you like to take a 15-minute break and then we will turn over the agenda to you at 8:15 to give you some practice of estimating forecast models?
Yeah.
Okay, good. I will see you then at 8:15. Thank you. I thought that you did a very good job of analyzing and explaining this forecast model. So that is worth 100 points of extra credit. If you would like to earn 100 points of extra credit as well, so next time I will give you another exercise that you can present to the class. Just one thing to note before you take on forecasting income and future stock. We saw that the ultra-regressive model that your son had estimated did not a perfect job, but fairly good. One problem with the model may have been that it does not adjust for non-stationarity. Here is the exchange data that your son had used, and you can see that there is a definite change in exchange rates going from March 30 to March 25, and then all of a sudden, the exchange rate jumps up after March 26th. So, uh, something has happened here to cause depreciation of the penny. I don't know the reason, but one possibility would be that the estimates of inflation in Kazakhstan usually come out at the beginning of the month. But anyway, uh, the time series breaks down into two parts. Here's one part, and here's the other part. The mean, the average exchange rate is changing over this 2 week period. That is, the exchange rate is non-stationary. Consequently, the difference in underestimate of the exchange rate because it is using data from the past when the exchange rate was a lot lower than it is today. So one possibility maybe the non-stationarity of the exchange rate time series throws off our forecast because we are using data that are no longer relevant to today. So one way to fix that problem is to use not the level of the exchange rate, but instead the first difference. By the first difference, I mean of the difference between the exchange rate at time t and the exchange rate at time t minus 1. Okay, overall, a good job by yours on. Thank you.
Thank you, sir.
So let's move on to the exercise. You have at hand, I hope, an Excel file. With income in Kyrgyzstan, gross domestic income in this case. So this is looking at the amount of money that has been earned by people living in Kyrgyzstan. We had an adjustment for inflation, but using a sum that assumed a correction for inflation. do you all have Excel available? You don't, I think you have it. And do you have Excel handy?
Yes.
Oh, okay, good. So why don't we all call up the data page of the business learning spreadsheet, and if you would, for the next 6 to 8 minutes, estimate the lag to GDI, since people use the lag as the independent variable in a forecast of gross domestic income in coming years. About 6 minutes for extra credit. So we will reconvene at about 8:32. Okay, let's take a look at how you did on the forecast. How did you estimate the lag in this case in Excel?
Draw a regression, create an auto-regression model.
Okay, good. And where you get the estimates for the lag of GDI?
You get it from 2001,
Good deal.
year 2001.
Good. So in this case, the data are proceeding into the future from 2000 to 2019. So estimating the lag involves nothing more than plotting the GDI values and then moving them down by one row. So notice that we have lost an observation to 2000, but taking a dependent lag. And then at the same time, I looked ahead and estimated the graph for the time series, which, by the way, is always a good thing to do in analyzing time series. So what did you guess about GDI? Is it likely to be stationary or non-stationary? It looks to me, I don't know if true, that the series is non-stationary. It is rising rather steadily over time, even though we have already corrected for inflation. So my guess is that we will have another forecasting model that will underestimate GDI, since it is using old data with low values of GDI that may no longer be relevant to the storm. The second exercise for you is to regress GDI on its lag. So remember that we will go to the menu for data, choose data analysis, and then go to regression and will pause for 5 or 6 minutes to give you a chance to run the regression model and to interpret it. So we will reconvene at about 8:42 in 7 minutes. For extra credit of about 10 points. Okay, thank you. Go to it. Okay, so let's take a look at how you did. By the way, does everybody have access to data analysis in ToolPak? If not, go to File, Options, Add-ins, and then it's a ToolPak. So let's see what you found out.
I have
Go ahead.
1.45
Uh-huh.
445 e to e plus 11. So that's the number in general when you.
Okay, so let's see, for the input wide range is for the dependent variable. In this case, from F10 to F29. And then the dependent lag is the independent variable from G11 to G29. I have removed the first year since we had a missing observation to the dependent lag there. It's always a good idea to check off label, since that will give a name to each variable. And then I'm going to put all this on a new page. And finally, take a look at the standardized intervals. So let's see. Interesting. Oh, I have a mistake in this.
I have a different outcomes. I think you haven't included one more data, or is that me?
Okay, let's look again at the regression table. Oh, I see the problem.
It should
Yes,
be
you're
19.
right, I have a mistake. You need to be moved entirely to first observation. There it is. Okay, good. Thank you. Back now to regression. So we begin now with F10, not F11, since I removed a row of observations. F10 to F28. And the same thing for the G column. And I'm still making a mistake. All right, thank you. This is not my day. I forgot to include the labels, although it took labels off. So the labels are on row 9. So to determine a variable, we go from F9 to F28. Yes. And the same thing for the dependent lag. There we go. Finally. Thank you for your help. So, what is your interpretation of this model? Ostensibly, is it a good model? Does it look accurate? Judging from R squared?
From the standard residual, as it does not have any value exceeding 2, it looks good.
No outliers, which surprises me just a little bit. And R squared is 98%. In other words, the model is explaining 98% of the change in GDP from one year to the next. A very powerful model. Oh, what about the intercept? Is it
It's negative.
significant? Go ahead.
Is it significant? Yes, I guess.
It is not significant statistically, since we have a t-value that is lower than 2 in magnitude. So the interesting, according to the model, there are no fixed effects over this period of 2 decades that help to explain TDI into the star. It all depends instead upon the past values of the economy. Very high to statistic. So that's curious. And so a model is income times t equal to the intercept that we can basically just ignore. Oh, let's account for it anyway. 3.1 times 10 to the power 9. And then the portion of the model that depends on the lag, 1.06 times the lag of GGI. Okay, good. So now the task is to go ahead and forecast YT. At 10 T plus 1. The T plus 1 is pretty funny. The data are ranging up to 2019. So take a few minutes now, let's say until 9 o'clock, to forecast GDP in 2020 using this model. Okay, so I will pause there and then we will resume at 9 o'clock. Oh, okay, we are still recording, okay. 3.66 times 10 to the power 11, is that right?
Yep.
Okay, so let's take a look. Sounds good to me. So our value is the intercept. I'm going to just refer to the original cell. So this is D17. That's the coefficient on GDI and D18 times the value of gross domestic income in, sorry, in the year 2019. And I have 1.45 times 10 to the power 11. So let me double check that value. Well, looking at the wrong data. So this is 3.27 times 10 to the power 11. 3.48. Does that look correct? Okay, so let's go ahead and run the model. So the forecast that I'm getting, I think it's the same as yours on 3.65 times 10 to the power 11. And finally, do you believe the estimate? Is that likely to be a good forecast, do you think? This is what to know about what happened last year. But see, the forecast is for higher GDI in 2020 than in 2019. However, last year, we were subjected to the coronavirus crisis that led to lockdowns. So it's a little hard to accept that there was a recovery in the spend rather than a recession. Nevertheless, a recovery is what our model is suggesting. In this case, the figures for GDI in 2020 have not been come out from the World Bank, so you don't have a direct way of checking that particular estimate. Okay, good. Questions? Answers? Okay, so there is an estimated problem for you to try at home next time. Forecast GDI in 2019. This is our ultra recessive model of AR1 because the one denotes that they have a 1 year lag in the model. And then estimate the 95% confidence interval. And then finally, check whether the actual GDI in 2019 falls within the confidence interval. Good for 100 points of extra credit next time if you present it to the class. Or 50 points if you prefer not to present. Just to run regression.
Can I ask a question? Is
Yes,
forecasting GDI for Kyrgyzstan again?
yes,
But don't we have a value already for 2019.
Exactly, yeah. So you have data already for 2019, so you can check the accuracy of the model against the actual value for 2019.
Oh, so you take the data until from 2001 till 2018 and forecast the value for 2019.
Exactly. Yeah,
Okay.
that's right. Good. In fact, let me add that point. So you go run the regression. This time uses data up to 2018 and then exclude the observation for 2019. I should say 2001. Since we have to delete the first year due to using the lag of the determined variable, we don't have a lag from 2000. So we will take the data from 2000 and throw it out of the model. Okay. Questions about the extra credit exercise? All right. So go ahead if you wish and read Angus Deaton's book, chapter 3, for next time. And however, please put most of your effort into writing the methodology section of the thesis proposal. So thank you. It's up to very well today, everybody. Thanks a lot. Until Friday, do widzenia.
Thank you.
Thank you.
Bye-bye.
Bye.
Thank you. Bye.
Bye.